We will be introducing you to the new shading models available in the Node editor individually in a series of videos to follow. Before we turn to the new shading models, however, I think it's useful to define what shaders or shading models are, what they are to an artist, and what the differences are between shaders and textures to computer graphic artists like ourselves. For understanding what shaders are to an artist, we can think of traditional art media to get a good general understanding. Most of us have seen crosshatching or stipple dot drawings where line or dot density was used on a flat surface to make the subject appear lit from a particular angle or reveal shape. A computer monitor is also a flat surface and the same kinds of things are happening. So just as crosshatch is the analog of a shading model to a pencil artist, Lambert diffusion, for example, is a shading model to a CG artist who uses 3D applications like Lightwave. Most of the shading models that have been of the most interest to the CG community so far aren't using rough patterns to depict shading like crosshatching does. There are those, but most of the focus and interest has been on using the computer's ability to define intensity and color per pixel to achieve a model capable of photorealistic or picture-like display. Textures, then, are most often used to define surface qualities other than light shading, such as roughness, color patterning, and etc., kinda like painting on a surface. You can use textures to express shading qualities using node networks, just like a 2D artist would do with a crosshatch pattern. In fact, it would be quite simple to use the node editor to create a network that shaded your object's surfaces using only a pattern like crosshatching. Here's a very simplified illustration that is doing just that. This network produces a single light simulation of the Lambert diffuse model that Lightwave used to be locked into, but expresses the shading in terms of a grid pattern applied as only two levels of luminosity, basically black and white, and without the pattern to fool us, is completely flat across the entire object, meaning the entire object's surface is just one solid color. This, of course, could be expanded on for a more complex and eye-pleasing effect, but this should illustrate the point of where the lines cross between texturing and shading. Textures, simply put, are just patterns. Textures can control the amount and application of a shader, but the shader is still defining the optical characteristics or physics of that surface's properties. Using textures to control the application of shaders is common and extremely varied, but such a thing falls more into the category of technique rather than feature. We'd like to stay focused on shaders as a feature of the Lightwave software. So that was textures and how they relate to shading. Shaders, specifically, are the mathematical models of the physical properties of light and its interaction with an object's surface. The way a rendered surface is constructed, it's useful to consider ambience, diffusion, and specularity firstly as primary attributes. Ambience is the global intensity of light, global and non-directional, akin to luminosity in a way. This is a lighting property, and, for example, in a traditional model, if you crank up the ambience, you'll increase the flatness of an object's surface shading. Diffuse, then, is surface interaction with directional light. Diffusion is also a lighting attribute. The shader is defining how the surface will respond to diffuse lighting. The Lambert diffuse shading model, as we saw in our grid example network, is an extremely simple model. It's basically just the cosine of the angle between the surface and the light. Nothing very complex. More physically correct models are both desirable and advantageous. Specularity is the same deal. It's the reflection of light sources. It's a lighting property, but again the shading model determines how, based on mathematical models of light intensity, viewer angles, surface angles, and etc. The blend shading model, for example, is a very simple approach to specular shading. We now have in Lightwave 9 more physically accurate models such as Cook torrents that allow a greater degree of control over these surface attributes. With this particular new model, the Lightwave renderer can now take into account surface imperfection, backscattering, rim lighting, retrolobe, and other nonlinear approximations of reflective functions. These all contribute to the optical properties of a surface. Moving on past the primary considerations, ambience, diffusion, and specularity, there is reflectivity and transparency to consider. What we're modeling here is light waves reflecting and refracting, but not from a light source. It's actually creating rays to fire back into the scene instead of at the surface, like the three attributes we just discussed. Of course, these initial concepts, in turn, lead to some of the more advanced shading models like subsurface scattering, occlusion, and etc. These advanced shading models are even more accurate models of surface diffusion, taking into account even more specific properties of light and surface interaction. As computers get faster and faster, it becomes possible to consider more and more of these kinds of specific properties, resulting in more and more accurate rendering abilities. Computer scientists started out with simple models like Phong, Lambert, and Blinn, but as better, faster computers came on the scene, more advanced shading models were developed in the quest for truer and truer photorealistic reproductions of the real world as we perceive it. The new shading system has been made completely accessible to third-party developers for the first time in Lightwave history. With the advent of version 9, Lightwave takes its first steps away from its locked shading model of the past. Before, Lightwave's renderer offered only a modified Blinn for specular shading and Lambert as its diffusion shading model. All surface aspects were expressed using these models alone. Now, as of version 9.0, Lightwave offers the flexibility to apply and even mix any shading model that can be coded, and on a per-named surface basis. NewTek has added many, and we'll be covering them in coming videos. Third-party developers, such as the IFW2 developers, are hard at work adding even more. As mentioned in a previous video, the various shaders are intelligently categorized by menu structure with regard to the aspect of the surface they affect, which we observe as the 4 shading channels made available in the new Lightwave 9 shading system. There currently are 8 diffuse shading models, including Lambert, Minard, Occlusion, Oren-Nayar, Theta, a NewTek original development, Translucency, and 2 forms of subsurface scattering, though while in a separate menu actually classify as diffusion shaders. They are Kappa and Omega, and are both NewTek original SSS shading model developments. 2 reflection shading models, Ani-reflections, which stands for anisotrophic reflections, and 1 simply called reflections. 4 specular shading models, anisotrophic, Blinn, Cook-Torrance, and Phong. And 2 refraction or transparency shading models, called Ani-refractions, which of course stands for anisotrophic refraction, and 1 called simply refractions. And with more being added even as this video is being made. These new models bring artists a greatly expanded range of flexibility and control over the render, making it easier than ever for Lightwave to provide precisely the look you want at render time, and for every element in your scene. So what are all those for, and what are the differences? That will be the subject of the next several videos to come on Lightwave's new shading system and its abilities. This concludes the introduction to, and an explanation of, shaders in the upcoming Lightwave 9.0.